Hi, this is Mr. Merrill, and in this video we're going to talk about how to transition from a velocity versus time graph to a position versus time graph. Most people are okay going the other way around. It's a little easier to go from a position versus time graph to a velocity versus time graph. You just look at the slope. But it gets a little trickier when we want to think about going this way. So, one of the things that I want to point out is thinking about what does a velocity versus time graph give us. Well, we talk about this idea about an area under a curve, but what is that giving us? And the confusion is that is not going to give us a position. It does not give us a position. What it gives us is a displacement. So in thinking about how to transition, we also have to keep in mind this idea that a position, a current position, is given by some initial position plus a displacement. So when we talk about area under a curve, a lot of students have confusion with what that means. So what we mean is the distance from the horizontal axis to the position of the graph. So we can sketch out an area. So kind of enclosed in this box here, and we'll use a different color here. Okay, so we can think about these as areas under the curve, or maybe a better word would be areas between the horizontal axis and where the graph is. So now these areas don't have units of meters squared. They're not physical areas. But they do have units, and we can think about what that is. Just like finding a normal area, we want to think about length times width. That's really where the analogy comes from. So let's think about this length here. What is this length? It's not a literal length. It's 2 meters per second. It's a velocity because it's on the vertical axis. And we think about this width, it's not a literal width. It's a time, 5 seconds, because it's on the horizontal axis. So again, what is this giving us? This is not going to give us a position, but this area underneath the curve can give us a displacement. We see that if we multiply these two numbers. So if we take 2 meters per second multiplied by 5 seconds, it gives us 10 meters. And again, that's a displacement, not a position. So I should say positive 10 meters because displacement is a vector. Now, why does this make sense? I'll take some time here to give an analogy that I normally give. Imagine you're in a car. You don't know what mile marker or section in the road you are on right now. But you do know that your car is traveling at 60 miles per hour. And you do know that you've been traveling at this speed for 2 hours. So you could know how far your car has moved in this straight line along this road. You know your car has moved 120 miles. But you still don't know what mile marker you're at. However, if somebody told you where you started, if somebody gave you an initial position, then you could find out where you're at currently by knowing how fast you're going and how long you've been going at that speed. So we come over here now starting with our initial position of -5 meters. And we want to think about it. So our displacement is positive 10 meters. So if we're at -5, and then 5 seconds later, we've traveled 10 meters, that means we're not currently at 10 meters, because remember, we started back at -5. If we start at -5, and we travel 10 meters, right now at 5 seconds, we're only at 5 meters. So we have these 2 points. Now, how do we know how to connect these? Well, what is this velocity here? This is a flat line velocity. It's a constant velocity. And we know on a position versus time graph that constant velocities look like straight lines. Lines whose slope or velocity is constant. Now it sounds like I'm repeating myself a little bit here, and I am, but hopefully that makes sense how we know these dots are connected by a straight line because the slope of this line is constant in the same way that the velocity over here is constant. So that's how we get the red portion. Now if we move on to this next segment with the green portion, we can think about the same thing. So this side here is now -1 meters per second. And this side here is 5 seconds. So again, we're going to get a displacement out of this. This will give us another displacement. So we can take -1 meters per second times 5 seconds, and that gives us -5 meters. So again, we play the same game where we think about, okay, I was at 5, I've displaced -5 meters, so that must mean at 10 seconds, at the end of this displacement, I was at 5, I've displaced -5, so at the end of this 10 seconds, I must be down here at 0. And again, how do I know how to connect these 2 points? Well, that velocity is constant. So in a position versus time graph, that segment of the graph should be a straight line whose slope is constant. Alright, so that's going to take some practice. It's not the easiest concept in the world to wrap your head around, but the main thing is, again, this is giving us displacement. That's all. We have to be given some initial position, add the displacement to find out our next position. And then connecting those two positions is just done with a straight line, because straight lines on a position versus time graph relate to constant velocities. Alright, I hope that helped.